While the world takes a little bit of a rest over the Christmas New Year period, we thought we would too, but we're not going to leave you hanging. We've dug into the archives and found a few of the biggest episodes of recent times. So sit back and enjoy those, and we'll be back with new episodes of Space Nuts probably in the middle of January. See you then.
Space Nuts.
Hi there, thanks for joining us. This is Space Nuts Q&A. My name is Andrew Dunkley, your host, and coming up on this episode, we've got a question about gravitational waves and the Big Bang. We're also going to look at a what-if question. Love the what-if questions, which is asking about the life of Earth, not life on Earth, the life of Earth if the sun never died. Interesting angle. And we're also going to look at time and dark energy. That's all coming up on the Q&A edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me once again is Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. How are you doing?
I'm doing as much as I can.
Good to be Q&Aing with you.
Yes, you too. Shall we get stuck straight into it?
Why not? Yes, why not?
All right. Our first question comes, I'm not sure if it's Bo or Boa. I'll have to listen more carefully. Here we go.
Hello, Fred and Andrew. It's Bo here from Melbourne. I hope you're well. I have a question for you, and it is not about dark energy, nor it is about dark matter, but it is about gravitational waves. It's a straightforward question. Did the Big Bang produce gravitational waves? As we understand it, gravitational waves are generated when two massive bodies, such as neutron stars and black holes, collide with each other and cause that ripple in the fabric of space-time. But when the universe has just began in infinite density and so forth, when it came into existence via the Big Bang, did it produce gravitational waves or echoes? And can we detect those echoes in space and time? Very much like the cosmic microwave background radiation that we see today. Anyway, I hope that makes sense. I'd love to hear your answer. Thank you very much.
Thank you, Boa. That's a good question. We talk about the Big Bang a lot. We get a lot of questions about it. And I mean, it was a massive event. We don't know why. We don't know a lot, but we know we can see that it happened through the cosmic microwave background radiation that's still evident today. But gravitational waves if the universe didn't exist at the moment of the Big Bang and was being created as a consequence of that, I'm not sure gravitational waves could have happened the way we understand them with other events in our universe. So, I'm not sure about this one.
So the thing is, Andrew, the universe was created in that instant of the Big Bang, and so you're right. In the conventional theory, standard Einsteinian physics, we imagine that time and space didn't exist before the Big Bang. So you've got to create some space for your gravitational waves to go through, which is kind of what
That's
you're
what
saying.
I'm thinking.
Yeah, and so yes, there was the instant of the Big Bang that created this singularity in time and space, followed by this period, was it 10 to the minus 33 of a second, something like that in duration, which we call the period of inflation, when the expansion really took hold, and the universe went from the size of a football to the size of a galaxy in something like 10 to the minus 33 of a second. And the thinking is, and I'm actually dragging this up from reading a few years ago, but that yes, that inflationary period, as we call it, would have created gravitational waves. Or maybe a gravitational wave. But
I was about to say, maybe just one big one.
That's right.
At that point.
But the issue is that it is a gravitational wave of very, very, very low frequency. So
Right.
the gravitational waves that we get from colliding neutron stars, for example, they produce waves which are basically have a frequency which is in the audio range, which is why we can, turn those gravitational wave signals into an audio signal very easily after you've amplified it up a bit and after LIGO has done its magic on it. And that's where we get this chirp signal of whoop, as two neutron stars or whatever merge together, and eventually, because they're spinning ever more rapidly, and so the frequency goes up of the waves that are being emitted, and then stop at a high point because that's where they've coalesced into a single object. Now, you can think of those audio frequencies. We might talk about something like 500 hertz as an audio frequency, or you could take 440 hertz as the frequency of the standard A note in the musical spectrum. So let's stick with 500 because that's an easy one. The period of time between one peak of the wave and the next is 1/500th of a second. And so if you think that's the interval of time of a characteristic gravitational wave from two colliding objects. Now, the issue, as I understand it, is that the interval between peaks in a gravitational wave produced by inflation is about the same as the age of the universe now. It's not 1/500th of a second. It's several billion years, perhaps even tens of billions of years. It's quite a while since I read up on this. So normal gravitational wave technology is simply not equipped to detect these low frequency, ultra low frequency gravitational waves. But there might be other ways of seeing them. And one of the things people have looked for, and I'm not really very well up on this, but there is a potential signal in the cosmic microwave background radiation, the flash of the Big Bang that we see that gives us what the universe looked like 380,000 years after the Big Bang. That's what we're seeing there. That radiation contains information not just on its brightness, but also on its polarization. That radiation is polarized, a bit like light can be polarized. And I'm not really drawing the links very strongly here, but I understand that there are links between very low frequency gravitational waves and that polarization signal. So it's one of the things that people are looking for to try and detect this polarization within the cosmic microwave background radiation. So it's not at all a daft question, but it's quite a complex answer.
Yeah. But the Big Bang itself could have initially been created one gravitational wave.
Yes, that's right. Yeah, that's more or less it.
Yeah. There you go, Boa. You're right on the money. It's just a matter of finding a way of seeing them. Is it possible these gravitational waves still bouncing around like the cosmic microwave background radiation?
Well, yes, but at such a low frequency that you don't actually know it's there. You've got to find other ways of detecting it, because there's not going to be any change in the gravitational wave signal over a human experimental lifetime if you've got a frequency whose time interval is measured in billions of years. Forget it.
Yeah, that's a tough one. Forget it. Right. Thanks, Boa. That's a great question, and thanks for sending it in. We've got a question from one of our regulars, Rennie, who is from sunny West Hills, California. This is a what-if question. Theoretically, if the sun were never to die, let's assume it's just never going to die, would the Earth eventually erode, decay, and die on its own?
It's...
Well, my answer is no, because we'll destroy it first.
It could be very different. I mean, so if what Ren is saying is that, yes, the sun, we know it's going to evolve over the next few billion years, and it will change, and that will eventually result in the Earth being swamped by the outer atmosphere of the sun, which might not be very nice for anybody left on Earth. But if that didn't happen, if the sun just went on its merry way, being a normal star. There will be a few things that will happen over that time scale, which we know won't happen because the sun turning into a red giant is going to overtake it. One of them is the tidal breaking of the Earth's rotation, so that it always faces the moon. So the Earth's day will change from 24 hours to something like, if I remember rightly, it's 42 days that it's about that length of time.
Whoa.
And that's it turning once, and the moon will go around the sky, around the Earth in the same time. So the Earth and the moon will constantly face one another with a month and a day, which are both equivalent to, I think it's about 42, 43 days, something like that. So that's going to change things quite a bit. So that would, certainly alter the atmospheric dynamics of the Earth. If one side's getting warmed up for 40 out of 20 days rather than just one day of day and night. So a lot of things change. The constant bombardment by the magnetic particles from the sun. I don't know to what extent the Earth's magnetic field might erode, but there will certainly be changes. Maybe.
Yeah. What about?
Sorry, go ahead.
Go on.
Oh, sorry.
No, I was just going to say, if humans were still around in that period, would we? Well, okay. No, let me rephrase. Would we adapt as these things changed and reached that point? Would we be able to adapt as a species and other life on Earth adapt to live in that kind of environment?
Well, it certainly is. All these changes are ones that take place very slowly indeed, and over kind of longer periods than the characteristic evolution time to get from one mutation to another, whatever that might be for humans. So yeah, they're slow, and I'm sure humans could adapt to them. We're a pretty adaptive species. We might also by then be capable of building the megastructures that might protect us from some of the sun's funny things going on. It's hard to know, really, isn't it? But I think generally speaking, I mean, Rennie's question's a good one. What happens if nothing happens to the sun? Does the Earth just sort of survive? It probably survives. It will be changed. We might find we're all living in plastic domes or something by then, rather than, because the atmosphere has been so messed about with. But yes, I think I'm an optimist that humankind would survive.
Yeah. No, it's interesting because, we know what's going to happen. We kind of know when it's going to happen. But if it didn't, it would create a whole array of new challenges for humanity, because we would have to learn to live in a very somewhat hostile environment, I imagine, because the planet would not be the same. And I can't imagine what it would be like to have a 42 day long day. Birthdays would be few and far between, wouldn't they?
They would, but we're gonna know what that's like very soon, because the day on the moon is 29 days effectively from one full moon to another. So yeah. So we've already got something like that in store for people to experience. It'll be very interesting to see what even the Artemis astronauts on the moon make of all that.
Yeah, very interesting. Rennie, that's a great question. Thanks for sending it in. Much appreciated. And next up, we've got Daniel. This is a sort of dark energy question, sort of.
Hey guys, Daniel from Adelaide here. There seems to be more and more discoveries lately in the very early universe that shouldn't be possible because not enough time has passed, like the size of galaxies or black holes. Now, I've got a far out theory I'd love to share. What if time and dark energy were actually the same thing? So we know for about the second half of the universe that dark energy has been accelerating its expansion. Could this therefore mean that there was less dark energy in the first half? And if that's the case, what if time actually went slower in the early universe? So from our perspectives, what took a really short amount of time actually happened in normal time, with normal being in quotes. I'd previously asked a question on the show whether dark energy is related to black holes. I think there was a paper around the time that kind of suggested that it was. And we know that black holes do distort time. So if time is part of the fabric of space, maybe dark energy is too, but it's actually one and the same thing. I'm expecting a very quick, simple no, but I wanted to ask anyway. Thanks.
All right. Thanks, Daniel. Is time and dark energy, are they the same thing?
Yeah, you never get a quick and simple no from me, Daniel.
No.
It's always a long, drawn-out, complex no. No, it's not always no. But I think in this case, your thinking's interesting. We've talked recently as well about the fact that this new controversial theory from Joe Silk et al. Over in Baltimore, suggesting that perhaps black holes, supermassive black holes came first. They were formed in the early universe. And that goes a long way to explaining the conundrum that you mentioned at the start of your question there, that a lot seems to have happened in the first few millions or hundreds of millions of years of the universe's existence. So we kind of understand the gravitational time dilation effects pretty well, and they're actually quite small from our vantage point here 13.8 billion years later. But you're right to make the point that dark energy only seems to have appeared over the second half of the age of the universe, but that's more likely to be it's because its measurable effect has only become apparent. We think that during the first half of the universe's age, the galaxies within the universe were close enough to each other. The gravitational attraction would have basically kept the expansion due to dark energy in check, the accelerated expansion due to dark energy. And so it's only when you get past a kind of tipping point where suddenly the mass of galaxies in the universe is not strong enough gravitationally to break the acceleration of the expansion. And by that I mean BRAKE rather than BREAK. It's not enough to slow it down, and so the acceleration takes over, and that's why it's a tricky thing just to try and tease out, and we've talked about this recently as well, whether the dark energy is a constant, whether it's something that's a factor that hasn't changed in terms of its release as space expands. It's because there is this added impact of the gravitational pull of the galaxies, stopping us from basically seeing the effect of dark energy, the accelerated expansion of the universe back in the early universe. So I think all those things are well and truly understood and kept fairly separate by the scientists looking at them, and by that I mean time and dark energy. So that's a long, complicated no.
Yeah. Okay. Daniel, when Fred says, I think these things have been long understood, that's his way of saying you're way off. way off the mark.
I don't know.
I'm only joking. But it's worth asking, because otherwise, obviously this is something people are thinking about. So it's worth asking these different questions to just see if it's a possibility. Well, thanks, Daniel. Appreciate that.
Great question.
If you've got questions for us, please send them in, because we could always use them. Just go to our website, spacenutspodcast.com, spacenuts.io, and click on the various links. The AMA link will give you access to text and voice audio, or you can click on the little, it's not purple, it's green. When did they change the color of that? Send us your, it's purple when you hover on it. There you go. Send us your questions on the right-hand side of our homepage, and don't forget to tell us who you are and where you're from. Fred, we're done again. Thank you so much.
Always a pleasure, Andrew, and I hope we'll speak again very, very soon.
It's a distinct possibility. Could be within 13.8 billion years, in fact. Yes. Thanks, Fred. See you soon. Fred Watson, astronomer at large, and thanks to Hugh in the studio for making our lives so much more difficult with these split episodes. But no, it's okay. And from me, Andrew Dunkley, thank you so much for joining us. Looking forward to your company on the next episode of Space Nuts. See you then.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.